In this lesson, we're going to study displacement reactions, what they are and why they occur. The theory behind displacement reactions is really very simple, but you do need to know your reactivity trends, particularly for groups 1, 2 and 7 to understand it. So if you need a refresher, here are the links to these videos. Now let's consider a very simple displacement. Think of the common salt and ionic compound sodium chloride in a molten environment. The sodium has donated one electron to the chloride to form an ionic bond, so both ions have their complete octet and are very stable and happy. But then along comes a rubidium atom. It's much higher in reactivity than the sodium, able to donate its outer shell electron much more easily and attracts the chloride far more. So the chemical reaction happens. The ionic compound becomes rubidium chloride and the poor old sodium is kicked out and becomes a normal atom again. It has been displaced. Often when the species displaced is a metal, it stays just as it is, a pure metal. This can actually be very useful because some of the less reactive and easily displaced metals are the precious ones, like platinum, gold and silver, so there can be value in displacing these from their ionic compounds or solutions. For example, solid silver can be obtained by reacting copper wire with silver nitrate solution. When quite a reactive metal is displaced, it will often try to react with other elements that happen to be around. Quite a lot of the time, that's oxygen from the air or hydroxide from water. Displacement reactions are often best studied by a solution chemistry. So let's look at what happens when a halide in solution is displaced. Here's some sodium iodide solution. In an ionic solution, like we have here, the iodide ions are colourless. Now we add some dark yellow aqueous bromine to the mix. It's going to turn dark brown, showing the presence of diatomic iodine. Now remember the reactivity of the halogens. When the iodine atoms are displaced by the bromine, they immediately seek stability and pair up with each other to create diatomic molecules. They don't try to react with any of the water molecules because energetically it's easier for them to covalently bond to each other, so both atoms can complete their octet. The reaction is this. Now here's some sodium chloride solution, and again we're going to add aqueous bromine. What will happen and what colour will the solution go? Not much is the answer. The bromine isn't reactive enough to kick out the chloride ions, so it simply stays as diatomic molecules in solution, and it lends its dark yellow colour to the solution. So why is it important to learn about displacement? Here's a real-life example. The thermite reaction is carried out by reacting iron oxide powder with pure aluminium powder. The reactants are mixed together and then reacted, often by using a piece of highly reactive magnesium ribbon and some magnesium powder. When the magnesium burns, enough heat is provided to overcome the activation barrier and off the reaction goes. The more reactive aluminium displaces the iron from its oxide. When it has finished, you'll see a lump of molten pure iron left behind. We used to rely on the thermite reaction when laying down lengths of railway track to fuse two pieces of track together, and in fact it is still used today to carry out repairs to existing railway lines.